So good afternoon, everyone. Welcome to today's Resilience of Autonomous Systems seminar. And I'm very pleased to introduce today's speaker, Nick Hawes, who is an associate professor at the Oxford Robotics Institute. Nick is also part of the Department of Engineering Science at the University of Oxford and a fellow of Pembroke College, Oxford. And he leads a research group that carries out research on problems in mission planning and decision-making for autonomous systems, with particular emphasis on goal-oriented, long-lived robots that are acting in uncertain environments. He is a senior member of the AAAI, an associate editor for the Journal of AI Research, and a group leader at the UK's Turing Institute for the area of AI and robotics. His talk today will be on mission planning for long-term autonomy in mobile service robots. I'm very much looking forward to listening to Nick's presentation. So whenever you are ready, please start.
Cool. Thank you, Radu. Thank you for the invitation and the lovely introduction. I'm going to start by sharing my screen, but before I do, I just want to say that, I talked to Radu about what to present, so I've got a bit of a talk structure, but I'm really happy to be kind of interrupted as we go. So I'm very happy to take questions at any point. I've only got a single screen, so I won't be able to see hands or chat or anything, so feel free just to kind of unmute and interrupt me and ask questions as we go. I'm very happy with that. And then if things get a little bit out of hand, I can manage the time and we can come back. So just to check, you want me to talk roughly 45 minutes and leave 15 minutes for questions? Is that the...
That would be fantastic, Nick.
Okay.
Thank you.
So I will try and do that. If we happen to take 15 minutes worth of questions during the talk, I'll just keep going. But either way, we'll be done by 4. Okay. So share screen, do this, do that. Perfect. Okay. So yeah, I think Radu's introduction covered most of the intro for my talk. So I can maybe just skip through some of this, but just a quick introduction on myself. Well, perhaps more on my research group. So the group I run at Oxford is called the Goal-Oriented Autonomous Long-Lived Systems Group, or GOLS Group. And we do work on a range of topics around sequential decision making. So mostly that means mission planning, so coming up with a sequence of actions for an autonomous system in order to achieve some kind of goal. A lot of that work is model based, so we work with systems that have models of their environment and plan or search or optimize within the space of kind of sort of actions defined by those models. But we also look at things like reinforcement learning and other forms of learning that you can integrate into these model-based approaches. So we look at mission planning. We do it largely from a model-based perspective. And we do that, we use those, we have a model-based perspective because we're interested in this kind of long horizon behavior. We don't care how a robot moves its fingers from, 2 centimeters in one direction. We care about a sequence of actions to achieve a goal, which may be minutes or months away in the future. So we really think about long-lived systems and long horizon behavior. So that's the kind of things we care about. And we work on a range of robots. We tend to think about both the kind of theoretical computer science aspects of actually kind of the algorithms and the models, and we like to deploy them on robots. So our work sort of straddles theory and practice in a way that I don't know, I try and use the actual application to robotics to motivate the modeling and the theory. So that's kind of the way we think about the world. So we have kind of 2 bits of the world we think about in conjunction that kind of couple together nicely. So the first one is planning under uncertainty, particularly with formal guarantees. So we think of the world generally using formalisms that relate to Markov decision processes. And we think about uncertainty because a robot's behavior is uncertain and a robot's interpretation of the world is uncertain in kind of many dimensions. So it's impossible, well, it's not impossible, it's better in general, as the history of robotics has taught us that quantifying uncertainty allows you to generate better behavior. And robots do that in their localization, they do that in their control, and we do it in the thoughts of mission planning. So we like to plan under uncertainty, and our history comes from being quite tightly coupled to people working on probabilistic verification and model checking. So we like to think about trying to form performance guarantees or formal probabilistic guarantees over the behavior of robots, assuming a particular model. So we do like to think about the kind of different types of behavior specification we can use for planning under uncertainty. So thinking about efficiency, quality of service, multi-objective, risk awareness, things like that. So various kinds of objectives you can place kind of alongside the ability to reach a goal. And we also kind of do this in a context, because it's robotics, and I mean, this is all largely part of AI in general, a lot of the models come from data, or they come from learning processes or observations that are gathered online. Again, in a robotic context, we can't know the way the whole world is going to behave in advance. Some of the behavior of the world must be learned, some of it must be observed at runtime. And so we kind of see these things as going very nicely together. We want to provide formal guarantees, but we want to provide those guarantees given a model that has been acquired from data or online. So in our work, we tend to find the bits of the models these robots use, and I'll be a bit more specific later on, come from some data-driven or learning process, and typically refer to either space, time, or some other important task metrics, such as energy or radiation in a nuclear context. And what we really want to do is, so that the kind of big picture, and we'll come on to a little bit later, is by having robots that live for long periods of time, they get more data that allow them to improve their models. So this online acquisition part is always running. And that means that the formal guarantees you're getting when you plan over these models get better with time. So that's the kind of whole pitch of the group, really. It's about saying, how do we couple these two fields such that through online model acquisition, we actually get better behavior because our models get more informed by the real experience of the robot. And then we can use planning techniques to actually exploit the kind of probabilities we've been learning, or the models we've been learning, in order to really be able to predict with accuracy the behavior of the robot over these long horizon plans. So that's kind of the big picture of what kind of motivates me in a research context. The talk plan that Radu suggested was first to go a little bit into some of this kind of long horizon or long-term autonomy work, and this is particularly, it's quite old work now, and if you've seen me talk before, you've probably seen me talk about a bit of it, which is, we worked on a project where we built and deployed robots for long-term autonomy in everyday environments from an EU project that I coordinated called Strands. So I'll start off by presenting that, and that's actually a very good motivation that leads me into a lot of the kind of more algorithmic work we'll talk about. Then I'll talk about within Strands how we did mission planning, so how we built and solved Markov decision processes to control the missions that the robots were following. And then with whatever time's left at the end, I will talk about some more recent work we've done on mission planning, and particularly focusing on mission planning where I think there's an interesting kind of resilience pitch. So given the topic of your TAS node, we'll kind of veer into bits of my recent work that I think are particularly related to resilience or reliable performance in risky environments under uncertainty. So that's where I kind of think, that's the area of kind of resilience that I think is particularly interesting. Okay, so what am I interested in when I'm talking about abstract? It's worth thinking about kinds of missions these robots will be doing when I talk about robot missions. And in particular, when I talk about long-term autonomy, I'm often about long-term autonomy in human populated environments or everyday environments. So environments where humans are comfortable, and we'd like to introduce robots in the kind of near to medium term, whether that's supermarkets, kind of less structured warehouses, hospitals, domestic settings, farms, factories, all over the place. So the key thing here is we want to introduce robots into environments that are not explicitly designed or controlled for robot application. So the robot has to be autonomous, it has to use perception, sensing to actually deal with the variation that's present in those environments. And those raise a whole bunch of problems for roboticists because we like our world structured and predictable. Humans are a source of uncertainty and entropy. So how do we deal with these environments? Well, my general belief in the best to do it is sort of captured by the fact that I'm using largely kind of sped up stop motion-y kind of videos, right? When you run things at this speed, you see the structure, you see the dynamics, you see things changing, but you see things like things that kind of remain the same as well. So that's kind of the idea. There's when you look at worlds like this and you look at the worlds these robots are being deployed in, there is some common structure that you can exploit, provided you can model it correctly. So that's what I'm interested in. How do we deploy robots? Oh, sorry, horrible flashing. Let's get past that. How we can deploy robots in these kinds of environments, exploiting the structure that's there and kind of accommodating the dynamics that occurs within that structure. So I'm going to do that by talking, I'm going to give you an example of how we've done that. In fact, talking about the project I mentioned earlier. So this was a European project called Strands. It ran from 2013 to 2017, I believe, with 6 universities and 2 industry partners or application partners. It was a large project, and the work in this was, we had an amazing consortium, an amazing team of people. So all the credit goes to them. I'm just presenting the highlights of some of their work. But the pitch of this is something really that maps back to the work I described earlier. What we wanted from these robots, these will be indoor service robots, was robust, intelligent, autonomous behavior. That's what we always want from our robots. And we wanted that really to give us the resilience or robustness to run for long periods of time in everyday environments. The argument there was, when in the future you go out to buy a bit of robotic technology, you expect it to run in whatever setting like you'd expect a printer or a photocopier to run, right? It's just a bit of technology. It should be able to perform its task indefinitely in the environment. Once you have that long run time, that isn't the end in itself. That's an enabler that allows the robot to learn more about the structure that appears around it. So if you think about this from a machine learning perspective, this is kind of an active learning task, or it's a data gathering task. And the longer a robot can run for, the more data it can get. And as we all know in AI, more data is better. You know, it's inarguable that more data gives you more ability to learn about your environment. And given that we're learning stuff, because we're doing robotics and we're performing kind of service robot tasks for humans, we don't just want to learn stuff. The learned models have to then be exploited in order to improve the performance of the robot or better adapt that robot's performance to the environment. And that should allow us to close the loop to generate better behavior again. So this kind of virtuous cycle of robust autonomous behavior, long run times, data gathering, learning and planning is kind of the way that we set up the project to try and deliver this on real robots in real end user environments. So this is something we achieved in a few ways. I would say that's the previous cycle that I showed you there was very much aspirational, and we closed that loop once or twice in a couple of sort of sub themes. Many other bits of the project only went partly around different bits of that. But within the project, we deployed robots into end user environments, and we deployed them there for long periods of time. So these robots charged their own battery, they managed their own task list, and there were no engineers, no computer scientists, no project members on site. So we went there, we set up the robots, we mapped the environments, we worked with the end users to determine what the tasks were, and then we left for these robots to do the jobs they've been programmed with and manage their own behavior over those long periods of time. So the work I'm going to show you now kind of covers work we did at 3 or 4 different sites where these robots were doing a range of different tasks. And I'll give you a quick overview of the tasks. But the key thing to bear in mind is that these robots are autonomous. They get a bunch of tasks. They have both a fixed task list, which are the things they have to do during the day or that they could do during the day. They can also deal with on-demand tasks that come in from users. So the users had kind of a web interface, both on the back of the robot that you can see there, and they could access it via their web browsers in the offices. And they could request tasks for the robots. The robots had charging stations. You know, they had all these sorts of things that they use to manage their own behavior. So kind of autonomous, kind of pure autonomy here. Robots managing their own lives, their own behaviors, none of us on site. And in fact, one of the challenging things is most of the sites we deployed the robots were probably at least an hour away from any member of the project. So if these robots went wrong, there was a major cost, which one of us had to get on a train or on a bus and go and find the robots, which, you know, that's a good way to make your robots robust, is making sure there's a high cost for someone having to turn up to fix it. So we worked in both, well, actually, I'll talk through these examples, but just to show you, there's a couple of different robots. And what I'm going to do is I'll give you an example, give you some ideas of some of the tasks they were doing. And then I'll start diving down into the kind of key mission planning and modeling parts of this work. I should say, again, feel free, if you've got questions, please do shout out, interrupt, or however you want. Cool. So there is a question from Simus, asking if the robots encountered unexpected situations. Absolutely, and I have a slide on that. So I mean, for me, the biggest joy of this work was the unexpected situations, right? When you're dealing with robots, and you're deploying robots into end user environments, mostly stuff is unexpected. There's very little expected stuff, but there's lots of interesting things that we can talk about there. So these robots did a range of different tasks, and let me show you some of them. So we were not there in this project to necessarily deliver useful robots. I mean, that was kind of the aim. So, but we also wanted to have the actual tasks the robots did be natural in the environment without requiring a huge amount of PhD and postdoc time to deliver. So one of the first things we did was develop an info terminal app. So this is in Haus der Barmherzigkeit, which is an elderly care facility in Austria. And we had this robot, this green robot here, that was able to drive around. So the robot did multiple tasks. One of the tasks was driving around with a screen which had news, weather, had the daily menu. And so residents of this care home were able to interact with the robot to actually kind of access information that was otherwise quite hard for them to access. So you can see some people reading the information off the robot. And this robot stopped at various locations and at various times, and it actually learned over time the best places to stop, because it was effectively, it got some reward for being interacted with, and it learned over time to increase that reward by scheduling its behavior in different ways. It's a nice example of how you could use autonomy in this long-term context. The end users in the site, when we asked them, what would you like a robot to do? And the receptionist at this site said, oh, the most boring part of our job, the most tasked part of our job is guiding people to appointments and offices. So we implemented what we called the Bellbot, which was a robot application where you could type in a location and the robot would guide you. This was almost never used. So all the videos I show in this talk are kind of, I like to think of them as nature videos, right? We had to go and find the robot and video it because the robot was autonomous. These weren't fake. They weren't, there's not someone in the background with a joystick. The only one that is staged is this one, because it turned out that the people controlling the robot found it even more boring to explain to passers-by how to use the robot. And so this Bellbot system never really got used in practice. So this is a friend of the project helping us by interacting with the robot. So this robot had a map of knew where the locations were, and it would guide people around the site to show them to particular locations. The most interesting application, I think, from the whole project was also triggered by requests at the care home, which was they performed this walking group twice a week, where the nurses took residents around the site to give them physical exercise. So these are people with a lot of age-related, both physical and mental frailties, and part of their exercise and kind of effectively stimulation, keeping them engaged, was taking them for walks. And the nurses found it quite stressful because they had to deal with both kind of motivating the group, managing the group, and kind of entertaining them. And they're like, well, if the robot could be part of the group, that would make our job easier. And so that's what we did. The robot would actually lead the group. The faster members could run up behind it, or not run up behind it, walk fast and press a button to make it move further on. It would also play hiking songs and sound effects and things like that as it went around the site. One of the great things here, so this meant that part of the nursing role was freed up by the robot, and then the nurses could spend more time interacting with the residents in the home. And this was a really interesting application, because if it wasn't totally reliable, they just left it behind. So the robustness of this system was important in two ways. One, the robot had to be robust while performing the task that you saw there. So we're going to jump that back to the beginning. The other thing is that the robot had to turn up on time. So these groups set off 2 p.m. Tuesdays and Thursdays. If the robot didn't arrive on time, they would set off without the robot. So you actually had to also manage the behavior of getting the robot to that location on time. I see a hand. Please do just shout out.
Thanks, Nick. Just a quick question. You made it clear that some of these things weren't used, and some of the things appeared to become useful in there. How, given that when we deploy a robot into a situation, people don't know what they're going to do with it, how did you go about specifying something to start with?
So what we tended to do is we went to the site a lot. Like, we tended to take the robot to the site and do a day of kind of show and tell and workshops, and we'd say, we're coming back in 2 months with this robot. What would you like it to do? And then people would go, the first thing they would say is, well, can you put an arm on it and do this? And we'd say, no, we can't do that. That's really difficult. And then after, a few hours of discussing, people would come up with some genuine things. We worked together to find the intersection between what was useful to them and what we could do with the resources we had available. And then we tried to work, and we learned a few things through this with the comms team and the management of the site to say, look, here's the information everyone needs before we turn up with the robot. Part of that might be risk assessments and data protection, and some of it is like, here's how you work with the robot. And in most cases, we would turn up and we would be there installing the robot and working, and people would just come up and ask us things, and we would show them. And then what you found is some people would not engage at all, and so they wouldn't know how to work with the robot. They wouldn't know what the robot was doing. But you got a bunch of people that would sort of adopt it, and then they would become an advocate for the robot, and they would explain to other people how to work with the robot and what the robot was doing. So we found that you ended up training a kind of core of people that were really wanting to engage with it, and then they would help the rest of the site understand it.
And so on, did you therefore find that what they wanted to do with the robot changed once they'd lived with it?
Yes. I think once they understood the limitations better, I think that was the key thing for us. So these systems are very, very restricted in what they can actually do. And it required a bit of creative thought for these people to understand the capabilities and how that would fit into their lives. And so I think we tended to find that after a bit of engagement, they would come up with better ideas. But a lot of people could also then refine the actual application that was there. So the walking group application here, we ran it for 3 years at this site. And the third year, we had changed all sorts of things, from the interface to the speed. We developed ways of the nurses interacting with the robot via flashcards and all sorts of stuff. So what you could see, I think the way I felt it happened is that the applications were kind of, they started off very sort of prototypical. It was like, it could do something a bit like this. It could have news, or it could look for objects. And then by the second or third year, they're like, well, I can see it can do this really well. So why don't it do a bit more like this? And I'd like it if it posted images to Twitter, or it said this while it was doing this. And they helped us kind of co-design from a kind of base. They could co-design the applications.
Thank you.
Sorry, I think I saw another chat. How do we deal with robots not completing the task? Does a human help to complete the task? I'll say a little bit more about that in a minute. So it depends on the task. Sometimes, most of the tasks, if the robot couldn't do it, it just gave up and tried something else. But there was a few cases where other things had to happen, but I'll get onto that in a minute. But yeah, please do keep asking questions. This is awesome. I should also say it's much more fun for me if you all ask questions, because then we can shape this to what you need to learn about. And we had a security application. So this was at G4S in some of their offices. They were interested in how these robots could work on security tasks. So here, what would happen? The robot would drive into an office. It would perform a 3D scan. It would do change detection, and from this, it would learn about where objects typically appeared. And we use this in various ways throughout the project. For example, posting blogs of where unusual objects were found. And we had an office how messy certain surfaces were. And so we had this robot maintaining a blog of whether the surfaces were clean or dirty. Looking, are people in the office on their own before or after office working hours? So there's quite a bit of kind of security themed tasks that were going on here, which I think is only natural when the robot's main way of interacting is with sensors. One of the examples there was learning about activities. So the robot would track people's movements and was able to identify kind of outlying activities. We had a strand of work led by Tony Cohn at Leeds, looking at learning and modeling human activity. And from the security perspective, they were very interested in, can we spot people doing unusual things? This was another example of something which sounded much better in theory than in practice. The data was so noisy, and in these offices, there really wasn't very many clear activities or clear unusual activities. So what we ended up doing was kind of detecting when people, more or less, there was activity in areas that was quite unusual. So this is an example of one of the unusual detections that we came up with. So I think it probably was that a human hadn't walked towards this cupboard before in our observation. And this is a person getting biscuits out of a cabinet and offering biscuits to the robot. So that does count as a reasonably unusual behavior in my book, but he certainly wasn't a security risk. Cool. So those are examples, a snapshot of the various tasks we did. There were lots of different kind of refinements of those things that we covered. So another question, can you schedule tasks at a specific time? What if there are more tasks than robots at the same time? So absolutely. What would happen is the humans actually had a Google Calendar where they could go and put tasks for the robot. We had a special form that they could fill in on the Google Calendar. We also had a few other web interfaces. So you could specify, please turn up and greet VIP 9 a.m. at the front desk. Please pass a message to everyone in Office 16 between 2 and 3 on Tuesday afternoons. So you can do time-based scheduling. We only ever had one robot at one site. So the robot effectively decided which task it was doing. And I'll say a little bit more about how it made those decisions a bit later on. So the robot could be oversubscribed and it would drop tasks if it couldn't complete them. We had a priority system baked in, but I wouldn't say it was the most robust. It wasn't, the priority system was not formally verified. I wouldn't guarantee that we could execute all those tasks. What we did is we tracked a whole bunch of data from the robot. So this is a plot from one of our earlier deployments, just showing the kind of daytime of the robot. So you can see the kind of time the robot was active. You can then start to see the different kinds of tasks it did. And so we were able to track like the sort of daily schedules of the robots after the fact as well. And we've got a big chunk of time. And yeah, okay, Colin says May 21st start of BST. Yeah, it could have been actually. So there's loads of interesting things you start to see when you look at the behavior like this that you haven't seen, and there's still new things coming on. You can also start to see gaps in the robot's behavior, which becomes interesting. You kind of go, oh, why is nothing happening there? Oh, some kind of bug. And one of the things we have was an edge explore task, which allowed the robot to gather data about movement and navigation in parts of its environment. And it only did that when it lacked certain amounts of data in its model. And so you see this purple one, for example, appearing locked at the beginning and not later on as it got more and more data. Other things were supposed to be scheduled at fairly fixed intervals throughout the day, things like object learning, object search. And it spent actually quite a lot of its time just waiting. So this dark green, it's either waiting at its charging station or it's waiting somewhere in the environment, gathering data to learn about. So yeah, nothing too academic to take from this, but it just shows you there's lots of data about what the robot's doing when. Allows you to see what requests the users are making. And one of the things we did in this project is we were really trying to focus on developing robust long-term behavior. So the worst case for us was that the robot would run out of battery. If the robot ran out of battery, then there was nothing you could do. You had to go to the site, you had to push the robot onto its charging station and restart all its software. The dream for us is the robot ran non-stop, managed its own battery, getting out of trouble. And so we really focused on trying to deliver behaviors like that. And what this graph shows is that, each column is one of our deployments, which was effectively a kind of experiment that we ran. And the height of the graph is the total number of robot hours, so the lifetime of the robot at the site in that year. And then that column is subdivided into runs of certain lengths. So the dark red is runs that are up to 5 weeks long. So that's 5 weeks of continuous runtime, continuous autonomy from the robot. The dark blue are kind of short runs, kind of 12 hours, a max 12 hours. So that might be, you know, the robot turns on, starts up its cameras, seg faults, and, you know, we have to restart everything. There's a lot of that. And so what you can see is as we get through the project, generally the amount of time we had with the robot at a particular location got longer and longer. And you start to see more of the red, orange, and yellow than the blue dominating these runs. If the Kenya run, you will see that there's kind of care and security for each year. So we had the kind of office environments, we had the care environments, and you'll see that there's no security for year 3 and year 4. And that's because we changed site and had all sorts of frustrating bugs at the third and fourth year for security. So the results are atrocious. So we had lots of time, but I left them out. And they were atrocious for reasons that are mostly to do with Linux network drivers. So it's not, I don't believe there's anything we can really say interestingly about science or otherwise from them. So I tended to leave them out. It's very hard to do a kind of robust evaluation and say what meant we were getting better at this. And there's lots of things here. So one thing is that the team of PIs and postdocs and students that were building software and deploying the robots got a lot better at knowing what they were doing. We also over the years focused on kind of we learned how to manage the trade-off of deploying interesting science on the robots versus delivering robust application. In the first couple of years, every couple of months, someone would come to me as the project PI and go, "Oh, I've got this brilliant new computer vision algorithm. Can I run it on the robot?" And I say, "Oh, what have you tested it on?" They're like, "Oh, I haven't tested it yet, but you know, I just uploaded. I just push it to GitHub, and I said, and I'm like, yeah, cool. Let's do some science." And then after getting burned a few times, we kind of went, okay, to be on board in later years, you have to have shown, you have to approve this in the robot in your own site, and we got a bit more robust about that. So there was better software engineering happening. But I'd like to think that the robot itself, some of the algorithms we were deploying on the robot was also making it more robust. And I'll talk about that. That's kind of the interesting software AI mission planning part. So the robot was learning from its environment, it was learning from experience, and it was hopefully getting better. But we as humans deploying robots were also getting better at building that software and knowing what needed to be done. I mean, I should say that, I mean, it's not really part of the talk, but these systems they're all running ROS. If you've used ROS, they're running 80 odd different nodes, so 80 odd different bits of software all running in parallel. The robots have, I think most of the robots are running 3 onboard computers, so an embedded PC running navigation and 2 sort of laptop class motherboards sat inside running all sorts of other stuff. There are so many things that can go wrong in systems that complex that it took us a good couple of years to even understand really how to debug and visualize failures and things like that. So we got a lot better at many of these things, which I think is all part of a resilience story.
Nick, is there anything you can say about the complexity then of the software? So obviously this is the amount of time it was running. Is there anything about kind of like the number of autonomous decisions made between restarts? Because obviously having a robot running for 12 hours and doing almost nothing,
yeah,
different than having it running for 12 hours and doing complex stuff.
Right, let's see if I've got that slide or whether I took it out. It's not in this talk. So we had 2 metrics. We had we ended up in our deliverables reporting kind of 2 or 3 metrics. One was lifetime. The other one was what we called autonomy percentage. So how much of the time was the robot actually doing stuff? Because exactly, it's kind of safety and aliveness or whatever. Like you can have a robot, it's just turned on, it's doing nothing. And so we also tracked the percentage of autonomous time, and that went up steadily throughout the robot's lifetime. Because as the robot got better at managing its battery, learned more about its environment, it could actually do more autonomous things. So we measured that and we increased that. The complexity of the autonomous system is whether it was doing anything more complex in that time over time. I think it was, but that was all embedded within those individual algorithms. The overall system complexity remained about the same, I'd say. But it did do, I think it's on a later slide. Oh no, it's here. Oh, but it hasn't got the numbers. So in the end, we executed about something like 23,000 tasks on the robot. Each one of those tasks, like a task instance, and each of those tasks required planning, execution, and running multiple nodes with some kind of autonomy in them. We had about I think in total about a year of continuous runtime, sorry, year of runtime back to back over the lifetime of the project, and a lot more than that, and hundreds of kilometers of navigation achieved. So a great deal of autonomy. I think what we got better at in the project is like slicing it into layers where we could make something fixed and know that works well, and try and only introduce the new complexity in pockets. Certainly beyond the second year, there was a framework for overall mission autonomy that didn't really change, and that allowed us to make progress from there.
Great, thank you.
Cool, no problem. And has anyone else got questions before? So I'm going to move on slightly now to some of the software we use to make it more robust, and to talk about some navigation and failures and things. But if anyone else has got questions around the general, what did the robot do part, then I can. Now's a good time to answer them. So we superimposed on top of that 2D map a graph. The graph is manually generated. We tweaked it within a couple of days of each start of each mission. The nodes are positioned as locations where the robot needs to do something, or as navigation routes in general. So this is a high-level topological graph. The edges imply connectivity between locations. They do not imply the route. So the semantics of the graph is effectively the robot can move between two of those nodes if they're connected by a black line. They can move between the two nodes without visiting an intermediate node. So it implies a kind of pairwise connectivity. On top of this graph, we could label the edges with different actions. So sometimes the robot just needed to move normally, sometimes it had to pass through doors, sometimes it had to dock onto charging stations. And we also had effectively the tasks that could be performed at different locations. So maybe it would do some activity learning, maybe the robot would do some object search. So that was all tagged to locations, to the nodes in the graph. One of the interesting things in the context of robustness and resilience is dealing with failures. So navigation is the hardest part of mobile robotics. And people will tell you it's a solved problem. They'll say, well, navigating indoors is easy. People don't do research on that anymore. And that's a total lie, because moving in dynamic human populated spaces is very, very challenging. We encountered many different types of failures, generally due to an intersection between what the robot can perceive and what is there in the environment. So in this case, the robot cannot see these chair legs. It can see the stick in the middle of the chair, but it can't see the chair legs. The robot's got a 2D laser scanner. It's got a 3D infrared camera on its chest. The legs of the chairs don't appear in the 2D scanner. And because they're black and rounded, they're not returning anything in the IR scan anyway. So that bit of the chair is effectively invisible. And so the robot hits it very slowly. It's got a very sensitive bumper, and so it stops moving. And that's a kind of failure that we encountered in many different ways. There's lots of interesting things I can say about this, but in the interest of time, I will skip on. One of the things we did, a large part of our work became recording the statistics of how and when the robot failed and how and when the robot succeeded. And what we did for navigation behaviors is we added in a help system. So if the robot got stuck, we used what we called monitored navigation to try and repair the navigation parts. So we had different types of recovery actions. The easiest one was kind of turn it off and on again, which would just restart the navigation, because typically the failures are transient. They're caused by people walking in front of the robot, and that works pretty well. If possible, we would try and backtrack. So the robot will have driven somewhere, had some kind of failure, and we knew that we should be able to safely reverse back the way we came and try again. So the robot would look behind it with one of its cameras and reverse backwards. That gets you out of many different troubles. And then if that's not possible, we start asking for help. And so these different color blocks show you for a particular type of recovery where that recovery was successful. It also shows you all the places where the robot failed. And what you see is failures tend to be clustered around areas. So doorways that are quite narrow, you can see down here. This was interesting. This is around a desk where the robot was supposed to image the desk and do some object recognition. But we'd located a node down here, and this pathway through the behind the desk was a bit too narrow. So you see failures happening in kind of predictable places over time, which you can learn from. The recovery system, which was not part of any of the science we did, but it was probably the most valuable bit of code that we wrote and probably didn't get publications for, was this monitored navigation system. Just to give you an idea, again, this is back in some of the early days of the project, we probably triggered the monitored navigation recovery system once every 60 meters of robot navigation. And that's a huge amount of kind of recoveries needing to come in. And it saved us, every failure is a possible robot gets stuck and run out of batteries. So that is really important for us. And that actually probably enabled us, that's been the largest ability to deliver on the long-term autonomy, was being able to detect failures in navigation and recover from them. And these request help columns you see here, was the robot asking the humans around it to help. So it was saying, help, I am stuck, something is pressing my bumper, please push me away from this obstacle, or please push me into open space, and press go. And that was really useful from an HRI perspective as well. By having the robot ask for help, it really brought people into its world. It really helped people understand the robot's limitations. It didn't help them super well because they would generalize a bit too easily. When they saw the robot recovering from failures, they thought that the robot could kind of recover from any kind of failure. So one example is in one of our later deployments, they built a glass door across a corridor without telling us. The robot didn't know the glass door was there until it hit it, which it did repeatedly. But because it was able to backtrack, someone would see the robot backtracking, they would come and open the door and the robot would go through. And it was only when they got sick of doing that did someone phone me and say, yeah, Betty's really struggling with the glass door. And I'd be like, what, glass door? Oh. So we had to come in and adjust the topological map around that. So, you know, these recovery behaviors really did help people understand the robot and work with it. Okay, to answer the question about like, how do these relate to unexpected incidents? I could talk for about 5 hours of unexpected incidents. But here's a nice picture of a series of unexpected incidents from the care home. This is now counting the number of triggerings of our monitored navigation system. So the number of kind of failures that occurred in navigation, 2016 to 2017. And we're just looking at a count. And these spikes, like the high values, typically correspond to things that were unexpected in the environment. So the first one, there was a Christmas market in the care home. And so they set up stalls in the corridors where the robot worked. Of course, we knew nothing about it. And the robot was trying to drive through locations that were covered by gingerbread houses and people selling baubles. In this case, so the robot's charging station was blocked by a chair. So someone was rearranging the furniture, put a chair where the robot needed to charge. And so every time it tried to go back to its dock to charge, it failed. Here, this is one of the nodes in our graph. Again, they've rearranged the furniture and put a node there. So the robot's trying to get there and it just keeps failing. Same down here, people rearrange furniture without talking to the robot handlers, things start to fail. And later on, actually, we started to have some failures with our motors. So some of the hardware of the robot started failing and it looks the same. So by tracking a kind of statistics, aggregate statistics of robot performance, you start to get some of these ideas. Okay.
Nick, so yeah. you mentioned nodes there. So this was programmed with very specific points to hit rather than be close to. So how much was it possible for robots to learn to avoid areas that were problematic? Obviously, things like the charger, I realize are completely fixed, but
so
how much flexibility?
Two answers to that. The first answer is, in terms of the locations they were going to, it was a bit awkwardly fixed. So in theory, if the node was part of a journey somewhere, they didn't need to go to the center point and could pass through a region around it. But the way that was implemented meant that didn't always. Typically, you needed to be able to plan to that location, but you could fail to reach it. For the target destination, like if you were stopping somewhere to take an image, you had to get to that pose. And this is an area where I think we actually published a paper on it about 2 years ago, planning to visit regions rather than visit points. So I think it's still a reasonably open problem in the motion planning literature. So I think it's quite an interesting problem. In terms of learning not to do it, that's where the mission planning comes in. So we've got all this data, and I realize I'm starting to hit the time, but I think we've had some discussions. So I'm going to eat into my question time a little bit and talk a little bit about how we do exactly that. So we've got all this uncertainty, all these failures. We've got data about all of them. And what we need, we've also got timing information. So every time the robot traverses an edge, we start and stop a timer. So what we can do is, what we did in the project is we wanted a planning model that would allow us to capture the failure rates and capture the durations of actions. And so what we did is we put this into a Markov decision process where the states and the actions were defined by the map and the task. So the stuff on the left there is hand-coded. The stuff on the right, the transition probabilities, the action costs, are learned from experience. So that's very much the kind of, this is the idea that we sort of looked at the beginning. We've got kind of structured representations. We're doing some online, where online is the lifetime of the robot, acquisition of parts of that model. So particularly success rates and durations of actions. And this would actually be directly encoded into a kind of state transition diagram for our robot. So the robot would know if it's going from location N1 to location N2, there's a certain sort of success rate that it should expect. And then we could plan our missions using this kind of model. So just to jump through this really quickly, we then specified using linear temporal logic the missions that the robot was trying to perform. So we could say eventually reach a particular location, or eventually have passed between two locations in your map. So we had a formal logic specification of the task the robot was trying to do, but this was being planned and executed on top of a model that was built from a mixture of the robot's map and its experience data. So the longer the robot ran, the more it failed in particular locations, the more it knew about particular transitions in its map. Then when we planned, let me just jump to this. So we solved this to get a policy. So we ran some standard algorithms on, well, actually, I'll say that in a minute. We produced policies by planning for collections of tasks to drive the robot around the map. And at any time, to go back to the earlier question about like, how do you schedule these things? At any time, the robot actually had a big set of things it could do, had a bunch of different tasks. And we would plan on this MDP for a conjunction of multiple tasks. So if the robot had to meet a VIP and image some areas and do the reading group, the walking group, those would all be in its kind of task list, and it would choose a subset from that to know what to do. And in order to make sure we took advantage of the learned information about the failure rates, we ended up with a kind of a multi-objective planning specification. And so we did this in a sort of in syntactic order. The first thing we wanted to do was be robust. So we maximized the probability of delivering the full sequence of robot tasks. So that effectively means avoid the areas where you think you're going to fail. So we did maximize probability over the set of tasks. And then we said, given that you've got this conjunction of tasks, just because you're failing at one bit, don't fail at everything. So you maximize probability, and then you try and do as much as possible. So we thought about progression. For those of you that know about this space of the world, we looked at a progression matrix over the automata from the LTL formula. And we said, we want to get through as much of that as possible, which effectively corresponded to the robot doing as much as possible in the world. And then after all of those things, did we say be efficient? So once you're maximizing probability and doing as much as possible, then try and do all that in as little time as possible. So we kind of had an efficiency specification on top of that. We solved this MDP using Prism. So we're building a kind of a policy for the robot that has probabilistic guarantees over its behavior. And those guarantees come from the models that we're learning. So we really took the data, the failure data, and put it into the mission planning models that the robot was using. And we used those at runtime for things like execution monitoring. So if you looked at the policy, you would have an expected time to complete a certain chunk of those goals. And we could use that to do things like stopping the policies early if it looked like we'd gone on way longer than expected. So we can use the probabilistic model once we've synthesized a policy to also kind of do things like which task can we complete with high probability and how long will they take? And we can use that information to select an ordering over tasks. So that's the kind of way we used a lot of that.
Maybe a quick question here, Nick. So if you aim for robustness as your top priority, then potentially the robot will not learn about certain areas of the environment because it'll avoid them, right?
Yeah, so we had a separate task generator that would generate tasks for the robot to do that allowed it to learn. So the robot didn't know whether, so the tasks it got initially were like, go here, do this. We would generate tasks that were like, pass over this edge, and that would be generated if we didn't have enough data. And that would have a slightly lower priority, but it would force the robot to include those things. So yeah, absolutely. If you try and be robust from the beginning, you're not going to have enough data to know what you're doing. So we had some effectively an exploration system that would force the robot to gather data.
Indeed. Thank you.
Sorry. So actually, I think that's a good place to end it. So that means we don't get to cover the new planning stuff, but I kind of expected that would happen. We've got about 10 minutes, I believe, to take questions. So I think now is a good time to pause to take more questions if people have them. Otherwise, I can keep talking, but I'm very happy to take questions as we go.
All right, Colin.
Thanks, Nick. I realise I have the tendency to dominate on this if I'm not careful, so I will try and restrict myself to just one question because I think this is fascinating. In terms of you're finding the optimals there with your MDP and your policies, can you give us any information about how you dealt with trade-offs? So what happened when you felt that areas were more important? Maybe you've touched a little bit on exploration, exploitation, but maybe other kind of trade-offs that you might have in this. Did you have anything like choosing off a Pareto front or? No,
so the next chunk of the talk goes on into there. So we ended up, because we wanted to try and solve for as long a time horizon as possible. The kind of the true multi-objective queries in Prism didn't scale very well for the kind of behavior we wanted to use. So this was done with we used nested. We had an implementation of nested value iteration that forced the priority order there. And then what we did is each task had a reward associated with it, and that reward corresponded to a priority. So user-generated tasks had a higher priority than going to get some more data. And then we computed the reward per unit time for the different policies that wrote. So we actually planned over different subsets of the available tasks. Basically, we did that until we ran out of thinking time. And then we picked the policy that gave us the highest reward per unit time. So it was a pretty hand-wavy way of solving it, but it was like scaling the kind of decision making there is very hard. So that gave us a way of trading off different task types.
Great, thank you. I think I'll just have to go off and read some of your newer work. Thanks.
You do. I mean, there's a paper now on battery on trying to take a high level decision over should we charge or should we not. So we've been monitoring battery and thinking just do we go and dock, and there we've done some work with Pareto funds that show you how you can be aggressive or how you can be conservative and how that affects the reward over a longer time horizon than we're planning here.
All right, Grisel, next question.
Yes, I was just wondering if you used a single MDP model or multiple for the different formulae.
So the way we did it is it was typically we had a kind of a base model. The way we constructed our MDPs on the fly. We had a kind of navigation MDP that came from the map, and then depending on what tasks were requested, each task would augment the MDP in different ways. So every time we developed a task, we typically had to build a little generator that would add some states or actions to the MDP. The other thing we did there is when we used the results, so I skipped over how we included the learning, but the transition probabilities and the costs were based on a time point. So we would populate the MDP for a particular time of day. So the states and actions would be the same if the list of tasks was the same, but the transition probabilities would be different depending on the expected execution time of the tasks. So that meant we had different MDPs for 9 a.m. to 2 p.m., for example, because people were more or less likely to open doors and the areas of the office would congest at different times. So yeah, we generated stuff online in each case. Does that answer the question?
I think it does.
Yes, so it also means that you have a time span for each of the models?
Yeah, so we typically planned for about 20 minutes of behavior. We didn't have a time horizon,
Okay.
but we ended up, there was a kind of a trade-off here between how long, we effectively realized that 20 minutes meant we could solve the basically produce a policy in less than a second. But once you extended that to say 30 minutes of robot time, the cursor dimensionality really started kicking in. So solving for about 20 minutes of robot behavior was a good kind of trade-off in terms of the complexity of the problem. And that meant we also kind of had these windows that we could query for our learning processes.
So potentially you could have multiple MDPs at different levels of time granularity to have a sort of master plan giving you a strategy, and then this 20-minute plan. Very interesting.
Yeah.
Seamus,
Thank you.
Had the question?
Yeah, thanks Nick for a very inspiring talk. So my follow-up question, I think you covered it partially, but I was wondering first, how do you include the data from the runtime observations into the updated MDP? So I think you partially covered that, but if you could shed a bit more light, that would be useful. And the follow-up question is about the safe policies. What type of safety considerations were included?
Yep. So the first one is what we used. We've done this in a couple of ways over the years now. At this time, what we had, there was a machine learning system called Freeman, developed from the University of Lincoln. A guy called Tom Krajnik ran it. And all of this was keyed in on the topological graph of the robot. So for every time the robot went over an edge, we would just log something that we called a nav statistic. So lots of data about the performance of the robot. And then when we generated our MDP, we would query this system and say, please give us for this edge in the map, give us a success for this edge in the map at this time of day, give us a success probability and an expected cost. And that was solved. They had a model that depended on time, and then they solved a regression problem within that model. So it was effectively a regression task in that model, and there was some interesting time varying properties. More recently, we've done stuff, for example, with just using kind of Bayesian estimation over various distributions. Nothing too clever in the machine learning perspective. The key thing for us is it's already operating over a discretization of the world that allows us to do the machine learning part reasonably easily. There are some interesting questions about what happens day one with your robot when you don't have data. That's something that I'm quite curious about. In terms of the safety, so in this part, it was only all we were doing was maximize probability. So there was no explicit safety. Okay, so in the formal notion of safety, we had some no-go zones. So in the formula the robot was taking, there was a bunch of co-safe LTL of doing this stuff, and there was some global avoid constraints. So do all this without going to these locations. And we populated that by there was occasionally people said, I get really pissed off when the robot drives near my desk. So if possible, we would add the locations near them to a kind of a zone that the robot wouldn't enter. But that wasn't necessarily an interesting safe constraint. The other things we've dealt with, and I guess in the interest of time, I'd say a lot of our newer work covers some of this. So we've now done some work on planning for safe battery constraints. So typically batteries get damaged if you go under a particular threshold. So trying to plan behavior while guaranteeing with high probability you stay over a threshold. We've also done some work on safe inspection in nuclear environments where you want to guarantee that you do not accumulate above a certain dose of radiation. And there we've been doing this kind of machine learning plus planning thing again with using Gaussian processes to model the amounts of radiation you're receiving. So you've got quite an uncertain MDP. So yeah, in this work, not a huge amount of formal safety, but so some of it was explicit. So we take the expected time and try and use that to sort of trigger fail, like to stop the robot doing things if we thought something was going wrong, but that wasn't planned in.
All right, thank you, Nick.
All right.
Thank you very much, Nick, again for this really insightful and interesting seminar and for answering all our questions. I think we are past 4 p.m. now, so there are still plenty of questions, but I think I will delay them until we have the opportunity to go over them in person.
Cool.
So thank you very much for giving the seminar.
That's all right. Thank you for the invitation. Thank you for all your questions. It was a pleasure to talk to you all. And yeah, please do just get in, if there's anything else you know, get in touch, or yeah, we'll see each other in person in the future sometime.
Thank you also to everyone who attended and asked these questions and participated in the discussion. So now our seminar series is entering a summer break, actually. So we will resume in September, and we will be in contact with details of dates, speakers, and topics in a couple of months' time. But until then, goodbye and have a nice rest of the summer.